Okay, any questions? A couple of people asked me some questions, so that made me think that I can give you a little broader perspective, what we are doing. So what we are actually considering like a point, wrong way. We are considering a point in a reacting flow, any point. Okay. So at any location, you have x, y, z coordinates, right? Or if you consider, say, cylindrical, then it will be r, z, and angle. Okay. So depending on the coordinate. Then in addition, you have all these properties. Okay. So you have P, the pressure at any point, consider any point. But then you also have del P there. Okay. So we are considering any point in the flow in the reacting. So what is del P? Okay, that represents the pressure force per unit volume. And then what is del P? How to write it depends whether it's a one-dimensional flow, or three-dimensional flow, right? Similarly, you have temperature at every point, and you also have gradient of temperature. Okay. So gradient of temperature, of course, contributes to the conduction term. Okay. Similarly, you have yi, and then you have the gradient of yi. Okay. So that contributes to the mass diffusion term. So just like temperature gradient gives you the heat conduction. Okay. And at every point you also have rho, the vector v. At every point in the flow you have mass flux and your momentum flux, your energy flux at every point. So that's what we are really considering. So when you consider this, when the volume shrinks, it becomes a point. Everything becomes a point. Okay. Main difference is, of course, density, pressure, temperature, kinetic energy, and what else? Internal energy. Okay. These are all scalar quantities. And then we have the vector quantities like velocity. Pressure is scalar, but when you write the force, it becomes a vector, because pressure force is determined by gradient of P. Okay. So everywhere you have these scalar quantities, vector quantities, and then stresses you have tensor quantities, which has 9 components. Okay. Everywhere in the flow. Okay, so now we can go back to the energy equation we were in the middle of. So we did this part. So we were here. Okay. So we were considering the work done by the pressure forces and then the viscous forces. Now viscous forces, again you have the normal stresses and the shear stresses. Okay. But the work done will be similar, because work done is just the scalar product of the force vector and the velocity vector. So the pressure, work done due to pressure comes as minus divergence of P times V, right? It's here. So this is also a vector. So this as we indicated, 3 components or 2 components are just 1 component depending on the, where it's a 1-dimensional, 2-dimensional. So 3 components will be then minus ddx, P, you can write it x1, pv1 minus ddx2, pv2. So now we are using 1, 2, and 3 for the 3 components. Okay. So, similar to this, okay, the normal stresses which are in the opposite direction, tau xx. Okay. So, we can write those as plus ddx tau xx v1 or tau 11 you want to use, maybe tau 11, tau x1. So, this is minus, this will be plus because pressure is in this direction, normal stresses are in the opposite direction. Then plus ddx2 tau 22 v2, so this is in the y direction, okay, and then the z direction, ddx3 tau 33 v3. Okay. So, here of course, I am writing everything. Okay. So, this normal as well as shear. Okay. So, these are the normal. Now, the shear for V1, it will be tau 21, because 1 is the direction of the force, okay, V1, and this will be tau x2, okay, because what is the area this is acting? Area 2, okay. So, area 2 means it will be ddx2, okay, and then x3 tau 31 V1. So, you see V1, 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 so there will be 3 there, okay. Similarly, you can write the other components, okay, there will be 4 more, okay, 3 here and then 6 here. So, this will be tau, okay. So, now if you consider V2, so 1 is here for V2, so then tau x1, tau 1 2 V2, okay. So, this way you can write all the components, okay. When you add all of those, you can write in this general form, or you can write in the using the index notation. So, in the index notation, this will be ES dot will be, okay, minus dp j Vj. Oh no, this is wrong. ddxj p Vj. Okay. So, j means you sum over all the 3 terms. Okay. Whereas now, the other components, you have tau ij, or let me change this to ji vi. Okay. So, first you are taking this tensor scalar product of this tensor with the vector, okay, and then you are taking the divergence of that vector. Okay. So, this will have many components, okay, 9 components. Okay. So, that is why it becomes a little more complex when you write the energy equation, because you have 9 stress components. So, you have to consider the work done by all those 9 components. Okay. Pressure, what else? The body force is straightforward. Just say whatever is the body force, okay, and then the scalar product of the body force with the velocity vector. Okay. So, this one also you can write as Fj Vj, if you want to use the index notation. Okay. Okay, now comes the fun part or the difficult part of the derivation, because the main idea, this is the equation E for E. So, E is internal energy plus kinetic energy. So, that is not the form we normally use for CFD or for analysis of flames. We use the form which is in terms of temperature. Okay, so, from here we have to go to an equation for temperature. Okay. So, you see now this E is U plus v square over 2. So, we need to first get the form for u. Okay. So, from E, we will subtract the kinetic energy term to get the form for u. And then we will get u, right? And then u will replace by h minus p over rho, PV or p over rho, because here we are considering per unit mass. Okay. So, there are two steps involved. First, try the equation for u and then for h. Okay. Once you have h, then you can see how do you write it for temperature. Okay. So, that is our final destination for the energy equation, writing it for h and then for temperature. Okay. So, the first step now is from this equation subtract the equation for kinetic energy. Okay. Because you see this term is ddt of rho E, not E, u plus v square over 2. So, if you can write the kinetic energy equation, subtract from this, we will get the equation for u. Okay. So, that equation you get by taking the momentum equation and then taking the scalar product of the momentum equation with the velocity vector. Okay. So, let us discuss that part. So, it is easier to see that using the non-conservation form. So, let us consider the left hand side for the, what is this? Momentum equation, right? So, if I take the scalar product with Vi, because this is a vector I, so I multiply by Vi. Okay. So, what is the first term? Oops, wrong. So, this will be rho ddt of okay, Vi over 2 or Vi square over 2. Actually, Vi square does not make much sense, it is Vi with the vector form. Okay. Or I will just write v square over 2. Okay. Because 2 will cancel when you take the derivative. So, this will give you the first term. Okay. So, you can use the same idea. So, what happens to these two terms is these are equal to rho ddt of v square over 2, because you have to realize this was a vector. When you take the scalar product, you end up with a scalar. Okay. So, this is a scalar, and then this will be rho Vj ddxj of v square over 2. Okay. So, you can see that you are getting the equation for the kinetic energy. Okay. Now, to get the conservation form of the kinetic energy, all we do is we multiply, we add these two terms. Okay. Because this quantity is 0. That is the mass conservation. So, now then I can combine this term and this term, that will give me this term. You can see that rho times ddt of v square over 2 and then v square over 2 times d rho dt. Okay. Similarly, these two will combine to give us this term. Okay. So, when you look at these equations later, you can do the simple derivation. So writing these two terms together. Okay. The right hand side is pretty straightforward. So this is the left hand side. When you multiply, you end up with these two terms, right? So let me just. So when you take the left hand side of the momentum equation, take the scalar product of VI. These are the two terms. Okay. So let's look at the right hand side. What do you have on the right hand side? Pressure force, and then you had the, let me use the vector for the index form, so which is dp dxi minus or plus d tau ji dxj. Okay, and then the body force is Fi. So if I now multiply this by Vi, okay, so those are the terms. So scalar product of V, okay, and the gradient of pressure, which is, you can write this form also, Vi times dp dxi. Okay. And this one now, okay, this times this. Okay, so this was a vector, then you take the scalar product with vector. Okay. And this, of course, is straightforward, Fi times Vi. Okay. Or you can write in the vector form. Okay. So this is, okay, the kinetic equation, conservation equation for the kinetic energy of the flow. Okay. Now, those of you who have taken like course in turbulent flow, we use this equation quite a bit, because from there we can get the equation for the kinetic energy of turbulence. Okay. When you break this into, the mean part and the fluctuating part. Okay. So all we now do is, we have this equation, energy equation already, which is E is U plus V square over 2. So we subtract this equation, the kinetic energy equation, from this energy equation. Okay. Subtract means you do term by term, right? So when you subtract this minus this, you'll end up with this. Okay. Because E is here is U V square over 2. So this term gets subtracted out. Okay. Rho V square over 2. Okay. Then on the right hand side, you have these three terms. I didn't write it here, so let me rewrite this. So you have, so here I already have the vector form, so why don't I write the index form here? So this is J rho Vj, and then you have U plus V square over 2. Okay. And let me write the kinetic energy, the left hand side here. Okay, so it's ddt rho V square over 2 plus ddxj rho Vj V square over 2. So that's the kinetic energy of, here you have times, all of this times Vi. Okay. So you can see now, subtracting this term from here, okay, this will cancel out. Okay. So that's the second term here. Okay. So this is the vector form, this is the index form. So this you can write as what's written here, rho U, rho V vector times U. U is the internal energy. Okay. Now let's look at the rest. This term doesn't change. Okay. That's the heat flux term due to conduction and species diffusion, right? This is the work done by the pressure forces. Okay. So if I write the index form, it looks like this, right? Okay. So this you can split into two terms, P dVj dxj plus Vj dP dxj. Okay. So you see in the energy equation or the kinetic energy equation, you have this term which cancels out. Okay. Yeah, don't get confused, with the index, because whether you use I here or j, it doesn't matter. Okay, because this is I and I, this is j and j, the same thing. Okay. You can use any index, call it q. Okay. Basically, these are three terms, right? dP dx1 times v1, dP dx2 times v2, dP dx3 times v3. So whether you write I or j, it's the same. So when you subtract, so see this term will cancel out from the energy equation. Okay. So here you have two terms. You subtract this term from this, you end up with P times divergence of velocity. So this is P times divergence of velocity. Okay. Similarly, you have one term here for the work done by the viscous forces. This will cancel out from this term. So this one also I can show if I write in the index notation. You have dd xj tau ji vi. So easier to see in the index notation. Okay. So I'm writing this term. Okay. So again, you can split this into two terms, vi tau ji dxj plus tau ji dvi dxj. Okay. So you can see that one of the terms, this term vi times this will cancel out when you subtract. Okay. And you are left with, in the u equation, you are left with this term. Okay. So this is not a simple vector, or this is like a tensor, because this is dvi dxj. When you say dvi dxj, right away it tells you it has how many components? Because I is 1, 2, 3, j is 1, 2, 3. So it has 9 components. When I say dvi dxi, then only 3. Okay. But those are, you add. Here you add only when you multiply. Okay. Because this is a tensor, 9 components. This is also now a tensor. Okay. So you have to add all those terms. There are many terms here. Okay. So if you really want to get deeper into this, okay, write down all the terms for using Cartesian coordinates. Okay. So finally, you end up with this equation for the internal energy U. Okay. So the rate of change of internal energy, this is the rate of change due to flow. This is due to conduction and species diffusion. Okay. And now this is the interesting part. The pressure work we had here, there are two components. One is here, which changes the kinetic energy. The other part changes the internal energy. Now this is a very interesting term, P times divergence of velocity vector. Okay. Divergence you write in the vector form like this, or dvj dxj. Okay. So Does anyone remember for the basic fluid mechanics, the divergence of the velocity vector indicates the flow compressibility. Because if you look at the species, the conservation of mass, so let me spend a little bit of time. What is this equation? Conservation of mass, right? Mixture mass. So if I write this out, rho, right? Okay. So somebody already told me what is this quantity in terms of, this is the total rate of change of density following a particle, right? Because a lot of times we write this as the total derivative, the local derivative and the convective derivative, So this is more, going into basic fluid mechanics, So this is the rate of change of density, and then you divide by this density, which is nothing but the rate of change of volume for the fluid particle, opposite of that. If the density decreases, then the volume will increase. So you see, this term represents the rate of change of volume of the fluid particle. So now come back here. This is what we call Pdv work. Remember, we just write change in energy is delta Q delta W, which is Pdv. So this is the Pdv work, because divergence of velocity represents the rate of change of volume per unit volume. It's like the percentage rate of change. So you see, this pressure work, part of the pressure work changes the internal energy, which is Pdv work. Other one changes the kinetic energy. So this is something we don't get unless you do go through the derivation. So this is the total energy. Some of the pressure work is changing the U value, some is changing the kinetic energy. This is the Pdv work which we are. So now it's making more sense. This is like delta U, left hand side. This is like delta Q, and this is Pdv. And then of course, if you have viscous stresses, this is like similar to Pdv from the viscous forces. So this is what we got for the internal energy. The next major step is change this. Here I'm showing again you can write this way, or you can write. I find this easier to understand in the index notation, because it's easy to write all the components. Here you have J and J, so you have 3 terms, right? Here you have J and I. So first write the 3 terms for I. So it will be tau J1 dV1 dxj plus tau J2 V2 dxj tau J3. So you got 3, and then you write for J1, 2, and 3. So you can write all. So now what I'll do is replace this U by H minus P over rho. So then you'll get the equation for H. So why you have to go through all these steps? Because H is not a real physical quantity. Internal energy, kinetic energy are. So when you do work done, it changes the internal energy or kinetic energy, not H directly. So now we write for H. So let's look at the first term. So it's ddt of rho u, right? So now u is replaced by, u is replaced by h minus p over rho. Okay. So what is this quantity? ddt of rho h, and what else you get? dp dt term. Okay. Similarly, the next term is, okay, let's use the index notation, dxj rho vj, and then u is h minus p over rho. So this one rho vj h, and what is the left? Minus ddxj of rho vj, no, rho will cancel, vjp, okay, ddxj of p times vj, okay. So this term and this term are, I am showing on the left hand side, okay. This one doesn't change, this term stays as it is. This one doesn't change, but this term p, what is that term? It's p times, so on the right hand side you have minus p times dvj dxj. So you see you have two terms here, one will cancel with this. Okay. So one will cancel with this, what is remaining here? Okay. That will be vj dp dxj. Okay. So on the left hand side you get these two terms, minus dp dt and then minus vj dp dxj. Okay. So what is that? Minus dp, so what is dp dt plus vj dp dxj? Okay, that's again the substantial derivative. So that is written here on the right hand side. Okay. So going from here, using this u h minus p over rho is pretty straightforward. Okay. Again, I said, you can use this form, it will be easier to see for you too. Okay. First time, I always find it easier to use the index notation. Okay. Now the very last step. Okay. There's already too many equations already. But now let's, okay, you remember the constant volume reactor or constant pressure reactor, we start with H, and what was H? Okay. H we write like this. Right? So we did exactly same thing for the constant volume, simple reacting system. So we do here now for the more complex three-dimensional flow. So replace this H by, okay, yi, sum of this yi, okay. And then of course, now we can write what is Q, okay, term. So then we have the equation for, okay, this temperature T. Okay. So that's on the next slide. Why didn't I write that? Because I skipped some of the steps in making the slides. There were too many equations to write. Okay. So let me show a couple of steps. So we are almost half an hour, so I think we'll be able to finish this section. So let's look at now this term, rho times h. Okay. So this is the time term we had for the constant volume reactor. Okay. Going back. So we didn't. Oh, I'm going too much back. So we had this term. What was this term? That was 0 for the constant volume because there was no flow. And this was also 0, except that delta Q, which is adiabatic system, it was 0. So it's much simpler, of course, for constant volume reactor. Okay. So now we use the same analogy there, same procedure. Replace this H by sum of yi HFI CPI dt. Okay. So if I multiply by rho here and then take the derivative to get this term. Okay. So it will be ddt so we'll get two terms here. One term, this one, when you take the derivative, and then this term. Okay, we did this yesterday, but there are two terms. So let me write it first. ddt. So let's do it slowly. So your rho yi. Let's keep it Hs right now. This is Hs. I. Okay. Instead of using the integral, so that's the sensible enthalpy. Okay. Is this correct? HFI. Okay. So similarly, from the second term, one will be HFI, other one will be HSI. Okay. So you can write those two terms. Nothing changes on the right hand side. Okay. So let me write those two terms. So ddxj. So you have rho, then Vj yi HFI plus ddxj rho Vj yi HSI. So everyone follows what is HSI? That is just CPI dt. Okay. So the sensible enthalpy. So now we can get rid of this term and this term using the species equation. Okay. Excuse me. That's on the next page, next slide. So you start with the species equation. So let me write it here. So rho yi dt plus ddxj rho Vj yi. Okay. On the left hand side, these are the two terms. Okay. So what I do is I multiply by HFI and then sum over all the species. Okay. Now HFI is a constant, so I can bring it inside the derivative. Okay. So then you see this term is same as this term, this is same as this term here. Okay. So after multiplying the species equation by h of I, okay, and then the right hand side is, okay, let's keep it mi triple prime. Oh, let me see what I used in the next equation. Yeah. So remember what is mi triple prime? This is wi dot times mi, okay, the chemical reaction rate term. So this gets multiplied by h of I. Okay. So you can see that this term is here, this term is here. So these two terms will be replaced by, okay, when you subtract, okay, by this term, which will appear as a negative term on the right hand side here, okay, because you are subtracting, okay, I have the only problem is the equation is on the previous slide, so you have to look at your notes. You know, when you are subtracting the enthalpy equation from this equation, so these two will cancel out. What is this term yi hsi? That is the same as hs. Okay, the total sensible enthalpy. So this is what I am writing here. Okay, rho hs, and then this term ddxj, rho vj, and this is hs. Okay. Okay, now bigger question is why I am doing this. Okay. Sorry? No, this is not for species. Okay, because HS is the one which contains the temperature. Okay. Look at the notes from yesterday, you know, for constant constant volume reactor, constant pressure reactor. We did exactly same thing. Okay. But it was much simpler. We didn't have to go through all this derivation. Okay. Because we had mdh dt. Okay. Plus we are using the mole fraction, so it was a little different. Okay. But when you take dhs dt, what do you get? Okay, we all understand what is hs, right? Okay. So I'll write it again here. It is sum of yi cpi dt, right? Okay. Well, because you have yi, then you have to write cpi dt. Okay. So then this will have yi, well, let me write sum. So sum of yi, probably ddt of this. Remember that? What is that ddt of cpi dt? Sorry? Okay, if you have cpi dt t reference to t, what is the time derivative of this? cpi dt by dt. Okay. So this will give you cpi ddt. And there will be, of course, another term. So that's the reason we are writing in terms of hs. Okay. Because really that equation is for temperature when you write it hs. Okay. So I just showed you as an example, dhs dt will contain Cpi dt dt. There will be other terms, of course. Okay. So this is, think of this equation as, okay. So what actually the common practice is, many of the softwares, they don't solve for temperature, this equation for temperature directly. They solve it for Hs, okay. Then Hs is, as I written there, yi Cpi dt. So once you know Hs everywhere, and of course you know yi from the species equation, then you can find temperature everywhere from this equation. Okay. So when you do equilibrium adiabatic flame temperature, okay, so you can go back and look at it. You do, more or less the same thing. You calculate the enthalpy of reaction, okay, and then you have terms like this for CO2, H2O, and then by iteration you calculate the temperature. Okay. So same thing you are doing here when you have three-dimensional reacting flow. Okay. You calculate, you compute Hs, and from Hs you get temperature. Okay. And then in Hs term also, okay. To fully understand, you can neglect every other term for a constant pressure or constant volume reactor. It will be just dH. So it will be. So let's write that equation for a simple homogeneous reactor. For homogeneous reactor, it will be rho Hs equal to okay. And what is this? This is W dot Mi. Okay. So now think about this. This is very similar to the energy equation used for calculating equilibrium temperature. Okay. Except now it won't be equilibrium temperature, it will be temperature as a function of time. Okay. Of course, now it's a reacting flow, so you have the convection term, conduction term, okay. So all the other terms. Now, a couple of important notes. Okay, here I have already replaced this Q. So you have the conduction, and then you have the enthalpy, okay, flow due to mass diffusion. Okay. So radiation is not included in this equation, final equation. But you can always include that. I made a note, radiation is not included above, but in most reacting flow, radiation is important. Okay. Now then there are two other terms here. Okay. So these two terms are important in some very high speed reacting flows, okay, like detonations, or if you have if you're considering the combustion instabilities, pressure noise, then these two terms are, especially this term becomes important there. Okay. Most flows we neglect these two terms, especially if it is okay. High speed reacting flows, we neglect this term. This term depends, whether you are considering, the instabilities due to pressure fluctuations, then we have to consider this term. Okay. But most high speed flows, this term is negligible. Okay. This represents this term when you write it out, because you can write the, what is tau? Those are the 9 stress components. So if you write all those out, this term is always positive and represents the viscous dissipation of energy. Okay. So like aerospace, when the space shuttle enters the atmosphere, it it generates tremendous amount of heat, right? So that's mainly this term, okay, the viscous drag we call, okay. So this is important only when you have high speed flows or when you have like lubricating, okay, very low speed lubricating flows, high gradients system. So normal combustion and reacting flow analysis, the like softwares we do not have this term, okay, unless there is a special situation. So for flames we are going to analyze, we will not have this term or this term, but rest of the terms we will have, okay. Whether we consider laminar flames or turbulent flames, turbulent of course analysis gets a lot more complex, because we do not consider HS, we consider then the fluctuating part and the mean part. So there is a lot of turbulent modeling involved for turbulent flows. But if you are doing like DNS of turbulent flow, turbulent reacting flow, then you can use these equations directly, okay. Now this one I give as an exercise in class. So this is the equation we got today. It's the same equation on this page, okay, except that we neglected these two terms now, okay, dP dt term and then the viscous dissipation term. Rest all are here, okay. So now physically, okay, this is the rate of change of sensible energy, sensible enthalpy. This is the change due to flow. This is conduction. Okay, now this is easy to understand. Now this is, okay, the species diffusion, sensible enthalpy changing due to species diffusion, and this is due to chemical reactions. Okay. Now for some cases people are using another form of the equation. So I usually give this as like a homework exercise, go from here to this equation. There are just a couple of, two simple steps, okay. It looks a lot more complicated here, but when you do it actually it's very easy to get to this equation. So that's another form which is used, and the advantage here is, okay, that you are not, see here you have temperature, but now this equation becomes exclusive for HS. Okay, that's the main difference. Okay, here you have divergence of lambda times gradient of temperature. Here you get divergence of lambda over Cp and delta HS, gradient of HS. Okay, so you are solving for HS anyway. And this also brings, okay, this important parameter Lewis number. Okay. So you all know what is Lewis number, right? Doing combustion. What is Lewis number? Well, it's here, but what is first of all lambda divided by rho Cp? That's the thermal diffusivity. So it's thermal diffusivity divided by the mass diffusivity. Okay. Now, traditionally we are not considered, we have assumed Lewis number equal to 1 when you do simple flames. Okay, but okay, the real flows, you have to consider non-unity Lewis number. There's a lot of work. Okay, all these okay, non-unity Lewis number effects come through, flame instabilities. Okay, I can show you a lot of very nice pictures of, flame instabilities when the Lewis number is not equal to 1. Okay. For example, we are familiar, a lot of us are familiar with the laminar flame speed, right? So the laminar flame speed which is reported, those are all for Lewis number equal to 1. Okay, if you have some other Lewis number, non-unity Lewis number, then the flame speed can also change. Okay, maybe others another time I can show you some results. Maybe I can show you one result on the effect of Lewis number. But basically here we are done. So let me just mention, because you will be looking at the slides. So if the Lewis number is 1, then this term will drop out. Okay. And if it is steady flow, okay, then this is known as the Schwab-Zeldovich formulation. Okay. So the Zeldovich, well-known, physicist or combustion scientist, Soviet Union. So he got this equation first. So basically, it's coming from here with Lewis number equal to 1 and steady flow. Okay. And it has a very simple interpretation, right? The rate of change of enthalpy, sensible enthalpy due to flow. This is due to conduction. Okay. And this is due to, reactions. And this looks very similar to the species equation. Okay. It exactly looks almost, same. Okay. Then they use, one-dimensional form of this equation, axisymmetric form for, different cases. I have the one, so this is the summary page, summary sheet, listing all the equations we discussed. Mass conservation for the mixture, species, okay, momentum. So this is for H, okay, and then for HS. This one or this one, those two. Then Schwab-Zeldovich. Okay. So basically, that's what we did, between yesterday, one session, and today. All these equations. Now, this is the interesting part. You can take these equations and you can get equations for the simple cases like constant volume reactor or constant pressure reactor. Or we did the Wellstad reactor. You can get that also. Starting with these, three-dimensional equations. This is the last slide. So for one-dimensional flames, premix flame, they use these equations. So this is the mass conservation equation. Species looks much simpler for one-dimensional case, okay, because this mass flux becomes constant. Okay. And then for enthalpy, they use this equation, or actually finally they use for temperatures there. Okay. I think this is the last slide. Oh, to make it complete, so you have these governing equations, and then you need transport properties and the thermodynamics. So yesterday, Professor Hiroshoge was discussing. So when you use any software, you have to supply, three other files: the kinetic data file, the mechanism, thermodynamic properties, and the transport properties. So this slide shows you this. Okay. So you need, okay, CPI values, HFI values, okay, and then the transport properties. Okay, they use equations like this. So this is what is used in Chemkin, so I'm just writing that part, but we discussed already some of these equations. Okay. The viscosity is also calculating using the viscosity of individual species. There is a typo, this is mu. Actually, it is a mu. It looks kind of u. So mu I is the viscosity of each species. Okay. And CPI, there is a polynomial, fourth degree polynomial. Okay. So a lot of these details are also, if you use like Chemkin or some other softwares, They usually supply more information. Okay, that's it. All right, I think I'll stop here. If you have any questions, we can discuss. So this was a little bit, like compressed. When I'm teaching fluid mechanics, the Navier-Stokes equation, we spend like 2-3 weeks. And that's just the Navier-Stokes equation, which is the continuity and the momentum equation. Okay. In heat transfer course, we go further, we have the energy equation, which is for temperature. So reacting flow includes everything: compressibility, thermodynamics, chemical reactions, mass diffusion. So that's why the equations look. Okay. But once you understand these equations, you can apply to any field, heat transfer, okay, or fluid flow, whatever, thermodynamics. All right.